Okay, thank you very much. So in my initial discussions with Mark Welland, we talked about how computing has changed the world over the last 60 years, and also how computing has changed over the last 60 years as well. And today I want to focus on changes to the way we have written, executed, and deployed software, and how this is likely to change in the future. However, we can't talk about software without talking at least briefly about the changes that have happened to computer hardware, since software requires hardware to run on. So let's start with two comparison points. Firstly, here is the EDSAC computer. It was built in the late 1940s in Cambridge and was the first practical program-stored computer. It was a machine built using the technology of the day. Vacuum tubes were used for the logic, and the working memory was stored as acoustic pulses transmitted down tubes of mercury. Program instructions and data were loaded from tape, and the result was output on teletype printers. The first program ran on the 6th of May 1949. Let's compare that against this, the Raspberry Pi 3. This is the latest practical program-stored computer designed in Cambridge. It was released in February 2016 and contains everything a modern machine requires, apart from the screen, keyboard, and some non-volatile storage. From the photo alone, you get a sort of qualitative sense of the change in scale, alluding to the significant changes in computing. But maybe it's the technical data that will help us compare and contrast the two better. So before we get into the details, it's worth noting that the EDSAC was one of the very few practical program-stored computers in its era, and so by definition was world-leading in terms of performance, whilst the Raspberry Pi was certainly not the world's fastest computer in 2016, rather it was one of the cheapest at around $35. So in the table I've listed here some of the major features of both hardware systems in common units. I've had to take a few technical liberties with the details, but the overall scale of change is clear. In terms of processing horsepower, the Raspberry Pi is around 1 million times more powerful. Main memory is larger by a factor of 100,000, as is the rate at which data can be entered into the machine. The size reduction is also impressive. We could fit around 100,000 Raspberry Pis into the same space as a single EDSAC. Power reduction is perhaps more modestly impressive, and partly driven by the fact that the EDSAC was a reasonably power-efficient machine for its day. The story of computing, of exponentials everywhere in terms of performance gains over time, is probably something that many of you are familiar with. I still think it's amazing when I look at the numbers myself. And yet I don't think it's the most intellectually profound thing the computer industry has done over the last 60 years. The model of computation is very similar between these two computers. Computer programs written in 1949 can, with some adaptation, be executed on the Raspberry Pi today. And similarly, at least some small programs written on the Raspberry Pi could have been executed on the EDSAC. So a clue as to what I think the more profound changes can be found on the component board of the Raspberry Pi 3 in the two highlighted boxes. Does any of you know what these components might be? So on the right-hand side, we have the Ethernet connector. On the top left-hand corner, we have the Wi-Fi antenna. And both of these enable connectivity to the internet. And these are crucial to the story of software architecture because it's computer networking which has really transformed our understanding and the use of computer systems and allowed some of the most innovative developments in software over the last 60 years. Now, this isn't to say that such a change could have happened if no progress had been made in terms of computing hardware. The EDSAC is hardly portable like the Raspberry Pi or a modern smartphone. However, hardware changes have enabled something, I think, that's even more exciting than the hardware shifts itself. Now, there are many measures we might try and pick to summarize and begin to understand the growth of the internet. Here are two simple ones which are widely quoted just to get us started. So first of all, we might look at penetration of the internet, or in other words, the number of users of the internet per 100 inhabitants. Well, we've broadly seen a linear growth in terms of number of users of the internet over the last 20 years, with around 80% of the developed world now using the internet on a regular basis. There is still significant growth to come, however, in the developing world, and where the majority is still not online. And in terms of global average, we've got over half of the population still to go. So we might also wonder what has happened in terms of the number of computers over the same period, or in computer science parlance, the number of hosts connected to the internet. Has this grown to nearly 2, or has something different happened? Now, getting data on this is a little harder for a variety of reasons, not least because our definition of connected is somewhat complex. For example, do we consider a smartwatch which is connected to a smartphone via Bluetooth, which is then connected to the internet via an app on the smartphone, as a device that is connected to the internet or not? So traditionally, one of the measures that we've been looking at is the number of hosts that are directly connected with a visible address to the internet. And the ISC has been tracking this for over 20 years. And up until about the mid-2000s, the growth looked exponential rather than linear. However, since then, connectivity appears to have fallen off. I suspect a more nuanced measure, which took into account the billions of smartphones, smartwatches, and so on, which are hidden behind our home routers and mobile network gateways, would reveal something much closer to exponential growth continuing to the present day. After all, maybe if you ask yourself, how many computers did you have 10 or 20 years ago, and how many do you have now, you might see some kind of exponential trend. So why do I think the growth of the internet is so profound? What's quantitatively different about the internet, which I suggest has not changed, which has not been the case with the developments of a single computer? I think the difference is the change in how we architect the software. From the 1950s until the 1980s, programmers typically wrote software to run on a single computer. Software may well have outlived a single machine, requiring it to be moved from one system to another with some recoding effort and so on. But there was rarely any coordination between machines while the software was actually running and operating. However, in terms of more recent eras, we have the term, my other computer is a data center, where the rise of the internet has changed our definition of what computing and what a computer is. So that today's software is typically split into many components which are run on many servers distributed across the internet. For example, in our mobile phones, we hold not only something that is 1 million times more powerful than an EDSAC, but also it has connectivity, which means it can call upon thousands of other computers to help it answer complex queries for new information in a fraction of a second. The offloading of processing has traditionally been called the remote procedure call, or remote API, where a client device, such as your smartphone or laptop, sends some data to a server somewhere on the internet to perform some computation and return a result. This mode of communication allows developers to write smartphone apps which rely on services and facilities provided by other companies or institutions. For example, if you wanted to write an app today which displays nearby restaurants, you do not need to manually trawl the streets, building a map of the road network and writing down laboriously where all those restaurants are. Rather, you can use existing data and existing systems from many other companies or from within your program. In other words, the architecture is different. As a developer, your program asks another computer program for help. And this program, in turn, can ask others for help. It's a living network of interconnected bits of software, which spans the globe. In some sense, this customization of data and compute power echoes some of what Greg was saying in his talk earlier. There's intense customization of data sets and display that then becomes possible easily through this technology. Now, it's probably best to look at this kind of thing through example. So let's consider a popular example today, the architecture of the World Wide Web. And it's good because the composition of services there happens at really serious scale. Let's take an example such as the Forbes.com website. Now, I've chosen this here not because it's in any way unique, but rather because it's typical and because I have some data on it that I want to show later. On the surface, we see a consistent rendered web page. There's a top news section, there's an advert, there's a picture. Under the hood, however, there's a complex ecosystem at work. And one complex part of it is the payment model for the web, which is largely driven by adverts. As the saying goes, we are the product, or rather our eyeballs are the product when it comes to the web. So the top of the Forbes.com website is occupied normally by this advert. Unlike printed media, different adverts can be displayed to each user every time the page is loaded. And this flexibility can be exploited to maximize the effectiveness of the advert space, and therefore maximize revenue. So for popular sites, advertising space is sold in real time to the highest bidder, and that bidding is done by a computer program. And the ad ecosystem provides the bidders with as much information on the person viewing the web page as possible in order to extract the maximum value from the proposition. So as part of this, unique trackers, some of you might have heard of them as called cookies, are stored by advertising networks in the browsers of the users browsing the web. And these then track the movement of those users as they go between different web pages and move around the virtual world. So here is an example, a somewhat simplified picture of what can go on in the world of web-based adverts. So in step one, the user's browser talks to a web server based on a URL the user has typed in. So for example, the user might have typed in Forbes.com and hit return, or they might have gone to a search engine and ended up at Forbes.com's web service. In step two, the user's browser downloads the contents of the web page and renders it locally on the computer. This page does not yet contain an advert, but merely a placeholder for the ad, together with details of the advert server the publisher has contracted with to fill the space and display the advert. So that in step three, the browser contacts the publisher's advert server for the missing advert, and the browser supplies any cookies that have previously been left by the publisher's advert server, enabling correlation of the user's browsing habits across other web pages which contract with the same company. This process often allows the user to be cross-referenced with other databases which detail other established customer relationships. So in step four, the publisher's advert server provides details of the advert space and the user to the advert broker. Advertising agencies can then bid on the space, and the information available via the publisher's data and also the broker enable bidders to determine whether the web page is being viewed by someone they already have an established relationship with. So, for example, an online shop might spot their customer elsewhere on the web, and they decide that they want to remind them that they were halfway through purchasing some shoes a few hours earlier, invite them back with an advert of those shoes to return to the shop and complete the purchase. The advertising agency may also be given a summary of the personal profile of the user of the web browser. So for example, if the user is logged in via Facebook, then Facebook has access to personal information which can be used to determine whether you might like a particular advert or not. And even if an explicit profile is not available, it's often possible to build up an approximate consumer profile based on things such as the web pages you visit. And this profile might include things like an estimate of your age, of your gender, of your social demographic, and so on. All that information, therefore, is available to bidders who can use it to determine how much money they'd wish to spend in order to display an ad. At the end of the auction, the highest bidder wins, and therefore in step 5, the winning ad is displayed to the user. It's quite a complicated process which involves many moving pieces between many parties that are not always fully trusting one another. And all of this happens in a fraction of a second. The bidding part alone, for example, is often regulated to take only 10 milliseconds, the time that the Internet Advertising Bureau recommends as the response time for purchasing advert space. So you're probably wondering, how common is this? How often does this happen? And what does it look like in terms of architecture? So here is some data for tracking one particular user for 10 days from a study done by Microsoft together with the universities of Southampton and Porto. In this visualization, we can see the browsing behavior of this single user, and shown in green are all the websites or services the user has connected to. So around the edge you can see many major websites that we'd normally look for, like Engadget, Forbes, and so on. Then shown in red and purple are the advertising servers and the site monitoring services that the websites have used as part of their construction of their system. And shown in blue is Forbes.com, and the blue arrows indicate all the services that Forbes.com's website contracted with during the time this study was carried out. So their advertising networks and monitoring systems are all there, and you can see there are a dozen or so of them. And all these networks find out about the user visiting a web page every time they go to Forbes.com. You can also see there's nothing really very special about Forbes.com. Each online service visited by the user, shown in green, are connected to multiple other online services in this graph, and that connection happens in real time. It's perhaps also instructive at this point to look at the data the other way around. So here we can ask how many sites are associated with any given publishing advert server. So here is what DoubleClick is associated with. No fewer than 60 websites in this user's browser history. Indeed, when researchers looked across all the data, they found that 99.5% chance of a user will become tracked by all the top 10 trackers within 30 clicks from a search result page. So very quickly, after using a computer for a few hours, essentially almost all your movements across the top sites are then tracked by this small number of people. There has been an ethical question for some time about whether this level of tracking and sharing of information about users is acceptable or not. But regardless of your position on this, I hope you all agree that this is a seriously impressive software ecosystem at work. Now that I've hopefully convinced you that building really rather impressive software systems is possible, perhaps we should talk about some of the other problems which might still arise. What work is there still left to be done? One of the real problems is that we can't write code that works correctly. Software has bugs in it. The situation is bad enough for your average user who is merely trying to get the software to work, but it's particularly bad when you realize that some people who write software are not good people. All software, because it has bugs, have latent vulnerabilities in there which can be exploited by an attacker. And the problem becomes a lot worse when we connect computers to the internet, since software bugs may then be remotely exploited, allowing a bad person to access a computer which they're not authorized to do. This means that many millions, or in some cases billions of devices today can be compromised when a vulnerability is discovered. And that attack can be done by a fairly small number of people from a small number of locations in a short period of time. So I call this state of affairs whack-a-mole security, named after the arcade game shown in the picture. So in the arcade game, the contestant has a big hammer, and they've got to hit the moles as soon as they pop up with their hammer. And that's the state of internet security today. We rely on companies who write software to issue updates to whack security problems before they're exploited. We want these problems to be fixed before the bad people start taking advantage of them. A recent example of this, a case of bad software written by bad people, is called Mirai. And given the location and topic of this talk, this word is rather aptly the Japanese for the future. At least that's what both Wikipedia and Google Translate report. I hope there aren't any software bugs in the translation. Mirai is a malicious piece of software which targets consumer devices such as internet-enabled cameras and routers. The software runs on those cameras and routers, and what it does is scans the internet, looking for other internet-enabled cameras and home routers. Once it finds one, it tries to connect to them using the default username and password configured by the manufacturer. You can think of this as software which automatically attempts to dial every possible phone number to see if it can get in. So if this username and password combination work, then Mirai sets up a copy of itself to run on the new device it's just found. This new copy starts hunting for further hosts to infect, and in this way Mirai spreads or infects hundreds of thousands of hosts across the internet. This is a bit like a virus spreading disease between humans. All those devices whose username and password combinations are known to Mirai are at risk. Now, it's unlike a human virus because a router in the US can directly infect a camera in Japan, or vice versa. In other words, the two computers do not have to be in close physical proximity, and that therefore this results in a quicker infection rate than we see in a human virus. The authors of Mirai, therefore, are able to control hundreds of thousands of computers on the internet. And Mirai allows those authors to issue commands to all the infected hosts. As you might imagine, the authors use this power for bad things. For example, in September 2016, Mirai was used to generate a flood of requests to the website of a prominent computer security journalist, Brian Krebs. So much traffic was created by Mirai that the website of his was knocked off the internet, even though it was supported by a major internet infrastructure company. A slightly different approach used Mirai to knock Twitter, Reddit, and Netflix off the internet in October 2016. Now, you might say that the problem that Mirai takes advantage of is trivial to fix, and you'd be right. If a manufacturer had simply used a different username and password for each internet-enabled camera or internet router, printed it on a label, and stuck it on the side of the box, this problem wouldn't have existed. So we might ask the question in different terms then and ask, how good are we actually fixing these kinds of vulnerabilities? Are we any good at that? For that, I want to turn to some work that I've done in Cambridge with colleagues Andy Rice, Daniel Thomas, and Daniel Wagner. So Device Analyzer is an Android app that we developed. We launched it in May 2011, and since then, 30,000 individuals have installed Device Analyzer onto their phone and contributed data to our research project. The app collects a wide variety of details on smartphone usage, including things like the apps that are installed, how much data is transferred, battery charging cycles, information about Wi-Fi connections, and so on. And we make some of this data available to third-party researchers. However, for the purposes of today's talk, I'll focus on 3 data items that we collect. And these are the phone manufacturer model, the operating system version, and the build number. And here the build number is a unique identifier for a particular version of the operating system shipped on the phone. So one thing we might ask ourselves in terms of these vulnerabilities is the Android ecosystem actually getting updated? And for that, we don't need data from the Device Analyzer project at all, because Google publishes monthly data about the API levels they see for phones connecting to the Google Play Store. So Daniel Thomas very laboriously went through archive.org and other online resources to build up the historical data that Google has published. And this is what the data shows. So we've got 2011 on the left through to 2016 on the right. And the scale on the y-axis is proportion of devices that are running a particular version of Android. So you can see that in 2011, API level 10, which had recently been released, about 20% of the devices were running that API level. And still we have a few percent of devices running that API level towards 2016. What this data doesn't tell us, of course, is how are these API levels changing? Is it the case that people are throwing old phones away and buying new ones? Or is there something else going on in terms of software updates? So for that, we want to ask, are devices getting updated? And for that, we don't have any other public data available, and rather we turn to the Device Analyzer data to answer this question. So here is an example from Device Analyzer where we've selected 50 handsets manufactured by HTC. So again, on the x-axis, we have time as our scale, and each of these little colored strips represent individual handsets in the data set. And the color of those strips indicates the version of Android these particular phones are running. And you can see there are many phones there running the same color OS version for many, many years. Not very many updates seem to get through. Similarly, we can look at other manufacturers. So here is LG, which has a slightly different profile. Here we have a bunch of phones or a cohort of phones that don't seem to change, whereas others we see quite quick and rapid shifting through Android API levels. And in fact, on this diagram, you can see little black vertical bars which denote changes to the build number, but not changes to the operating system version. This indicates that probably this is a critical either security fix or bug fix for that phone handset. However, we don't really care so much about updates as fixing vulnerabilities. And what we'd like to understand is which phones were vulnerable to which discovered vulnerabilities. So when we looked at disclosed vulnerabilities, we could then make a note of which versions of the operating system were vulnerable. In other words, we could put phones into one of these three categories for each day. So we can mark a phone green if there were no disclosed vulnerabilities which affected that version of the operating system on a particular day. We can mark a phone as yellow if the operating system was vulnerable to a particular disclosed vulnerability, but we'd not seen this build number in the wild in the device analyzer data before the date of discovery. In other words, this phone might actually have some kind of patch for that vulnerability. And finally, we can mark a phone as red if the version is vulnerable, if that version of Android is vulnerable, and we also saw the build number actually in our data before the date of discovery, and therefore it cannot contain a fix. We can then take all this data and plot the daily proportion of device analyzer phones against time, showing how these three categories change. This is what you get. So on average, 85% of Android devices in our study were vulnerable to one or more critical vulnerabilities over that period. In other words, we're terrible at whacking security moles today, at least for Android. Now, most phones do indeed run for months or years without being patched. And this is not to say that Google is doing nothing. Far from it. The reason that the Android platform is not completely riddled with malware is because of the variety of mitigations that they have deployed and developed. But these methods are not as comprehensive and robust at providing updates. And I only hope that we ensure that regular updates start to flow before these mitigation strategies start to fail. So I hope that I've now convinced you that the software ecosystem today is extremely complex. There are already difficulties with understanding what happens to our personal data, and this situation will only get more difficult as the Internet of Things take off and yet more data about our personal lives is captured by computers. And since we don't know how to write bug-free software, we also need to think about how to operate in a world where the security of software will become increasingly important to our well-being and perhaps even our survival. How do we cope with the next 1 billion devices being connected to the internet? You might like to consider what happens once we connect our electricity meters, our hospital infusion pumps, and our nuclear power stations. What happens when our internet-enabled cars or Piaggios become self-driving and run software? We're essentially building a global robot with a vast array of sensors and actuators connected into the physical world. And these systems rely on software and services that are also spread far and wide across the internet. Remember, all these programs talk to other programs which use data from other programs to operate. The whole thing is integrated into a big mesh. These systems will be no more isolated from the physical world than they are from each other. Leslie Lamport once remarked that a distributed system is one that prevents you from working because of the failure of a machine that you've never heard of. If we don't improve our security, we'll know that when the Internet of Things is in full swing, when the tentacles of our global robot regularly cause harm and destruction. However, I don't want to end on a bleak outlook. There are lots of things we can and should do. Perhaps at least for some systems, we should consider whether they should be connected to the internet at all. And for the rest, we need to fix the incentives. There's a reason why the security of our internet-enabled cameras and smartphones are not patched. And that's what economists call negative externalities. There's no incentive for the company who made the device to fix it when vulnerabilities are discovered. After all, if you're running a company and you had 100 engineers, would you deploy 10 to work on fixes for devices already sold, or would you use them to make your next product 10% better? Of course, we would like to write bug-free software, and for this process to be cheaper than writing buggy software. But unfortunately, this solution simply does not appear to be on the horizon. So we're left with regulation to fix the market failure in computer security. I'm not the only one to suggest regulation as a solution. Bruce Schneier has been calling for this in the US for some time, for example. And Ross Anderson has remarked that we should demand all internet-enabled devices support a patching process before awarding a CE mark, thereby preventing their sale in Europe. A more indirect method is to regulate for transparency. I've previously advocated for increasing transparency around which devices get patched, not because consumers will care or use this to inform their purchasing decisions, but because the additional data helps experts, as well as corporate buyers and regulators, to know where the problems are. So, in sum, we've come a long way in the last 60 years, and we've got a lot to do if we want the next 60 to be as successful.